Hello everyone. Now we are going to see about the common ion effect. First, it is important to define what the common ion effect is. The common ion effect is a shift in an ionic equilibrium caused by the addition of a solute that provides an ion that can take part in the chemical equilibrium. So is the shift in an ionic equilibrium caused by the addition of a solute that provides an ion that can take part in an equilibrium. So some of the species that can provide the common ion includes common ion sources. Common ion source can be strong acid, like for example hydrochloric acid or nitric acid or hydrobromic acid and the like, or it can be a strong base like sodium hydroxide or potassium hydroxide, or like calcium hydroxide and the like. And the other option can be soluble salts like for example sodium chloride, or it can be sodium acetate, or can be potassium bromide and the like. These are classified as strong electrolytes. They are strong electrolytes because they can dissociate into ions completely. Okay, completely. This is the reason behind. So the ionic equilibrium can be created by an ionic equilibrium can be created by the dissociation of weak acids. Okay, weak acids like for example it can be acetic acid, or it can be hydrofluoric acid, or it can be nitrous acid and the like. Since these are weak acids, they partially dissociate in water, producing a chemical equilibrium. So here, when acetic acid gets water, it can dissociate very slightly, forming acetate ion, okay, acetate ion and hydronium ion. So as you can see here, since this is a weak acid, it produces a chemical equilibrium. So this common ion species comes here and affects this chemical equilibrium. The common ions can be produced from this species, strong electrolytes like strong acid, strong base, and soluble salts this species produces a common ion that can take part in this chemical equilibrium. So the effect of common ion, the effect of common ion is explained based on the Le Chatelier's principle. The Le Chatelier's principle. This principle states that if a species that can take part in the chemical equilibrium is added to a certain reaction in a chemical equilibrium, it will affect the position of that equilibrium. For example, some of the factors can be, temperature can be a factor, concentration can be a factor, pressure for gases, P for gases can be a factor that affects the position of chemical equilibrium. But our focus is on the effect of concentration on the chemical equilibrium. These common ions will affect the concentration of the species in the equilibrium so that the equilibrium can shift either to the reverse direction or to the forward direction. So let's see some of the examples that affects the chemical equilibrium. Look here. Let's see the original reaction to be the dissociation of acetic acid in water. See, this is a weak acid. It partially dissociates and forms the acetate ion and hydronium ion. Now, consider a solute like sodium acetate is added to this equilibrium. If sodium acetate is added to this chemical equilibrium, what will be the effect? First, since this is a strong electrolyte, when it is dissolved in water, it forms acetate ion and sodium ion. This dissociation is a complete dissociation producing the same number of moles of the reactant that is dissolving in the water molecule. So look, so this sodium acetate will create the acetate ion, which is a common ion. This is a common ion because this ion is found in the original chemical equilibrium. So look, there is acetate ion in the equilibrium. There is acetate ion which is found in the solute, sodium acetate. So now this is a common ion. So when sodium acetate is added, automatically it produces acetate ion, and this acetate ion will affect the concentration of the acetate ion in the original chemical equilibrium. So now, according to Le Chatelier's principle, according to Le Chatelier's principle, the addition of the acetate ion to this chemical equilibrium will cause the equilibrium to shift to the left direction. So equilibrium shifts to left direction, to the left. This in turn causes the concentration of the acetic acid, to increase. The addition of one of the product species in the equilibrium causes the equilibrium to shift to the left direction, causing the concentration of the reactant to increase. Now the concentration of acetic acid increases and the concentration of hydronium ion decreases. So the decrease in the hydronium ion in turn causes the pH of the solution, the original solution, okay, the pH of the solution to increase. This implies that the acidity of the solution, okay, acidity of solution decreases. As pH increases, the solution is approaching more of towards a basic character. So acidity on the other hand is decreasing. So the addition of sodium acetate to this chemical equilibrium causes the solution to be more of basic or to decrease its acidic character. This is the effect. On the other hand, this is the first case. And if we consider the second case, if, for example, if hydrochloric acid is added, okay, if hydrochloric acid is added, since this is a strong acid, it completely ionizes to form, okay, H3O plus aqueous plus chloride minus aqueous. So still there is a common ion. This is a common ion. This is a common ion because this ion is also found in the original reaction here. Okay, it is found in the original reaction here. So the effects are one thing, equilibrium shifts to left direction again, and concentration of acetic acid increases, and the concentration of acetate ion decreases. It decreases because as the hydronium ion increases, it will react with acetate ion, forming the acetic acid. So continuously the hydronium ion consumes the acetate ion, causing the reaction to undergo in the left direction. Now, when we see the concentration of hydronium ion, the total concentration of hydronium ion, increases because the hydronium ion increases because since this is a strong acid, it will add more amount of hydronium ion to the chemical equilibrium. So the hydronium ion increases, causing the pH to decrease, making the solution becomes more acidic. Okay, more acidic, more of acidic. Now let's continue on the effect of this addition of hydrochloric acid to this chemical equilibrium. This is the original chemical equilibrium. So the addition of hydrochloric acid causes the concentration, the equilibrium to shift to the left direction, one thing, and the other, the concentration of acetic acid increases since the equilibrium shifts to this direction, producing more of the reactant species, and the concentration of acetate ion decreases because the added hydronium ion consumes the acetate ion, producing the acetic acid, and the concentration of hydronium in general increases because more of the concentration of hydronium now is contributed by this hydrochloric acid. Since this is a strong acid, it can produce much amount of hydronium ion. So the concentration, the total concentration of hydronium ion increases as compared to the original reaction that can produce this hydronium ion. So now the increase in the hydronium ion concentration in turn causes the pH, okay, the pH to decrease. pH decreases. This means solution becomes more acidic, Okay, we can even roughly understand that the addition of strong acid to a given solution can cause a decrease in pH because it is causing the hydronium ion to be added more in the solution. Now look, let's see another effect. If for example, potassium formate, not acetate, and potassium bromide are added, what will be the effect on the position of the chemical equilibrium in the original reaction. Look, all these salts, okay, these are salts, okay, these are salts, soluble salts, okay, these are soluble salts. These soluble salts, okay, can produce, in the first case, the potassium formate produces hydronium ion, not hydronium ion, formate ion, aqueous, and potassium plus ion. So no common ion. No common ion and no effect. No effect, okay? No effect on equilibrium in this case. No effect on equilibrium. So there is no common ion by the addition of this potassium formate. On the other hand, if potassium bromide gets water, okay, when it gets water here, it forms K plus aqueous plus Br minus aqueous, bromide ion aqueous. Now still here, no common ion, no common ion, no common ion effect, in short, no common ion effect, that means. So look, the addition of such kind of salts to this equilibrium has no effect on the position of chemical equilibrium. Now, when you look at the application of common ion, okay, the application of common ion is it can help us to prepare a solution of known concentration. Okay, the concentration that we want can be prepared by the addition of this common ion effect. So look, the common ion effect it helps us to prepare a solution of known concentration. A solution of known concentration. Now let's see the mathematical part of regarding this common ion effect. So let's see an example that helps us to illustrate the common ion effect. The question is that determine the concentration of acetate ion and the pH of a solution containing 0.1 molar acetic acid and 0.1 molar of hydrochloric acid. Okay, this is the question. Look, determine the concentration of acetate ion and the pH of a solution containing 0.1 molar acetic acid and 0.1 molar of hydrochloric acid. Here, first, the chemical equilibrium is created by this acetic acid because it is a weak acid. Here, the substance that contributes a common ion to the chemical equilibrium is hydrochloric acid. This produces a common ion. So first, let us produce the chemical equilibrium from acetic acid. When acetic acid gets water, it will partially dissociate and form acetate ion and hydronium ion. Now, the common ion created by hydrochloric acid is hydronium ion. Look, that is, hydrochloric acid gets water, completely dissociate and form Cl minus aqueous plus H3O plus aqueous. Look, this hydronium ion is the common ion. This is a common ion. Now, the initial concentration of hydrochloric acid is 0.1 molar. And the concentration of chloride ion that can be produced from this 0.1 molar hydrochloric acid is 0.1 molar, and hydronium is 0.1 molar. The reason is because since hydrochloric acid is a strong acid, it completely ionized, producing the same concentration of a species, negative and positive species, from this dissociation. Now look, now let's come to the chemical equilibrium. So in the chemical equilibrium, first we need to write initial concentration, change, and equilibrium. Change and equilibrium. Now the initial concentration of acetic acid is given, that is 0.1 molar. So first we need to write this concentration in the initial position. So the concentration of water is not important here, and here the acetate ion initially is 0, hydronium ion is 0. Okay, before dissociation of acetic acid, nothing is produced. So we have to make it 0, 0. Now change, we have to make a small amount of dissociation of acetic acid to be X, so minus X, and this is plus X. So if a small amount of acetic acid is converted into acetate, the same number of mole of acetate ion and hydronium is produced. This is observed from the chemical equation, the coefficient of the chemical equilibrium. So this is plus X, and again this one is plus X. So the equilibrium should be the sum of the concentration of the initial condition and the change condition. Okay, so it becomes 0.1 minus X, and this is X, 0 plus X, X. Now, the equilibrium constant of acetic acid is given, which is found to be 1.8 times 10 to the power minus 5. This is the equilibrium, the dissociation constant of the acetic acid, 1.8 times 10 to the power minus 5. So the chemical equilibrium Ka of this reaction can be written as the concentration of acetate ion times the concentration of hydronium ion divided by, that means the concentration of product over the concentration of reactant, that is it. So the concentration of acetic acid here. So this is the Ka expression of this equilibrium. Now we have to put all these given values to this equation. Now we get 1.8 times 10 to the power minus 5, which is equals to the concentration of acetate in the chemical, in the equilibrium condition is found to be X, and that of the concentration of hydronium is also X, divided by the concentration of acetic acid at equilibrium is 0.1 minus X. Look, now, since acetic acid is a very weak acid, it dissociates very slightly. Usually, less than 5% of the acid is dissociated. This means we can ignore the concentration of the acid that is dissociated into ions. So this X must be ignored, or it is approximately 0. So we can make this X as approaching to 0. So now it becomes 1.8 times 10 to the power minus 5, which is equals to X squared over 0.1. So now X squared is equals to 0.1 times this, it is found to be 1.8 times 10 to the power minus 6. So x is found to be 1.8, the square root of 1.8 times 10 to the power minus 6. This is found to be all right. So there is a common ion here. This is the concentration if we don't add this common ion. So now here the common ion is producing 0.1 molar hydronium. So here we have to make it around 0.1 molar here. So here this concentration, the equilibrium concentration is found to be x plus 0.1 molar. Okay, so here why we add 0.1 molar in place of hydronium initially is that because there is a common ion that can produce 0.1 molar of hydronium. So we need to write this 0.1 molar in the initial condition. Okay, so so the sum of 0.1 molar and that of x is x plus 0.1 molar. So now here it is found to be the concentration of hydronium is found to be x plus 0.1 molar. So again this implies that this one is also approximately 0. This x value is approximately 0. So we'll get x times 0.1. So 0.1 x እናገኛለን. So first we need to cancel out the 0.1 by 0.1. So we'll get, okay, sorry, it must be 1.8. Okay, x will be 1.8 times 10 to the power minus 5. So this is the value of x. X means it is the concentration of, this is the concentration of acetate ion. So the concentration of acetate ion, okay, the concentration of acetate ion, okay, is found to be x and is equals to 1.8 times 10 to the power minus 5, yeah, molar. This is the concentration of acetate. Thus the concentration of hydronium is somewhat different from acetate, which is x plus 0.1 molar. This implies that x is 1.8 times 10 to the power minus 5 plus 0.1 molar. So we can approximate this. This number is very small as compared to 0.1. So this gives approximately 0.1 molar. So this is the concentration of the hydronium ion after the addition of this common ion, okay, that is caused by hydrochloric acid. Here, the pH of this solution is found to be minus log the concentration of H plus. So this is equals to minus logarithm of 10 to the power minus 1. So this is found to be 1. So this is the pH of the solution after the addition of the common ion. So it is expected that if this common ion is not added to this chemical equilibrium, okay, if this common ion is not added to this chemical equilibrium, the pH is expected to be greater than 1, or it becomes very large, okay. So this is the reason behind. So for the sake of summarization, today we tried to see about the common ion effect, and the common ion effect is defined as it is the shift in anionic equilibrium caused by the addition of a solute that can provide a common ion that can take part in the chemical reaction. If that solute doesn't add any form of common ion, so it will not have an effect on the position of equilibrium. So next time we'll see about buffer solution. Thank you very much.